Hello everyone, I'm Pratima Samineni representing Group 18. So today we are going to explain about the two research papers which is based on search algorithms, and the second paper is severe weather avoidance using informed heuristic search. So here are our team members, myself Pratima Samineni, Gautam Kumar Nalluri, Murali Krishna Bomishetty. So coming to the abstract part of the first research paper based on search algorithms. So artificial intelligence search algorithms are used to find out the problem of shortest path finding. So the search algorithms are divided into two types. One is uniformed search algorithms and informed search algorithms. So again, the uniform search algorithms are divided into six parts. There are a breadth first search, a uniform cost search, depth first search, depth limiter search, and bidirectional search. And the last one is the iterative deepening depth first search. We're coming to the informed search. There are two types. One is the best first search and the A-star search. So there are few parameters to find the comparison between all these search algorithms. They are complexity, optimality, and completeness. So, and also there are few search algorithm terminologies such as search, search tree, actions, transition model, path cost, solution, and optimal solution. The properties of search algorithms are completeness, optimality, and the time complexity and the space complexity. And these are used to find the comparison between all the search algorithms. Well, coming to the introduction part, so as we all know, artificial intelligence is a large field of study. So it has a subset of machine learning, deep learning, and the data science, as we can see in this diagram. So mainly the artificial intelligence includes problem solving, knowledge and reasoning, advisor search, uncertain knowledge and reasoning, and expert system. So what exactly all these are? The problem solving is also called as the search techniques, while the knowledge and reasoning includes some resolution, knowledge representation, and fuzzy logic. But coming to the adversarial search, the example for this is a game playing includes minimax algorithms and alpha beta pruning. Uncertain knowledge and reasoning includes uncertainty, probabilities, and Bayesian networks. So coming to the next slide, which is a search algorithm approaches. So as I discussed earlier, like we are having a two types, uniform search and the informed search. So uniform search is also known as a brute force search, which includes BFS, DFS, uniform cost search, and iterative deepening and bidirectional search. It doesn't have any information about the steps to reach from current state to the goal state. And also to reach the goal, this search follows the optimum path rather than finding the other bidirectional or something path. It follows the optimum path. But coming to the informed search, it is also called as the heuristic search, which uses one function called as a heuristic function to solve a problem. It uses the two approaches. One is a generate and the other one is a test approach. This search includes hill climbing, steepest hill climbing, and A-star, AO star, and BFS algorithms. What exactly the heuristic function is? This function is used to estimate how close that a given state is from goal state. It takes the agent's current state as input and outputs an estimate of how near the agent is to the objective. It is represented with h of n, and it calculates the cost of an optimal path between the pairs of the states. Here we can see the equation to calculate this search, where h of n is the heuristic cost and h star of n is the estimated cost. This function acts as a model which leads to the goal state. It travels the search tree based on the next node using one function to reach goal state from present state. Well, coming to the next slide, which is a breadth first search algorithm, which follows the FIFO, like first in, first out model. So to reach the goal, this search expands the first level of its nodes and then the second level. This search has the time complexity and the space complexity as represented here, where B is the branching factor and D is the solution depth. So in this search, it has both open list and the closed list, as we can see in the diagram in the left side. So it has the open list and the closed list, where the open list contains a set of nodes that are about to explode, and the closed list has the set of nodes that have already been explored. For example, here we can see in the first diagram, at the level 0, we have number 1. The 1 is considered as a closed in the open list, and the children of 1 are considered as open list for the level 2. The queue is filled with the children of nodes 1, 2, 3, and 4. Then, using the first in, first out technique, node 2 is extended and the children of node 2, 6 are added to the queue. So this is all about the breadth first search, which follows the FIFO model. Well, coming to the another search, which is a depth first search algorithm, it follows the LIFO, like last in, first out technique. In this search, to reach the goal node, DFS first expands the source node and goes to the deepest node. It is also known as a recursive algorithm. DFS uses a stack data structure for its implementation. The process of this algorithm is similar to the BFS algorithm. And here are the time complexity and space complexity for this. By looking into the diagram in the right side, initially the node 1 is extended at the level 0. The stack is filled with children of nodes like 1, 4, 3, and 2. Here it is also having the open list and closed list. Then using the last in first out technique, node 2 is extended and the children of nodes 2, 6 are added to the stack. Then the node 6 is enlarged. It will go back to the beginning because it doesn't have any children. Here we can see in the diagram. And the node 3 will be enlarged as well we can see here in the closed list, we are having the 3 number. So it will follows this process and completes this. And while coming to the next search algorithm, which is a uniform cost search. So in uniform cost search, the expansion starts with the node having the low cost path. So it is having the cost on the edges for every node. So there are few parameters used to calculate the cost of every node. They we can see here the equation which is used to calculate this search, where C of M is the cost of current node and C of N is the cost of previous node. C of N comma 1 is the weight of the edge. Here we can calculate the cost using this equation and we can fill out this open and closed list. Here are the time complexity and the space complexity for the search algorithm, where C is the optimal solution cost. So while observing this diagram and the open list and closed list, we can see that the UCS is used to solve any graph or tree where the optimal cost is in demand. It is implemented using the priority queue. It gives maximum priority to the lowest cumulative cost first. Like UCS is like the same, it is similar to the BFS algorithm if the path cost of all edges is the same. It is optimum because the path with the least cost is picked in every state. It doesn't care about the number of steps, it only care about the path cost. So this is all about the uniform cost search. While coming to the last one in the uniform search algorithms, which is this is the informed search algorithm, A star. So A star search is the most known form of the best first search. It also uses one function to calculate the path, like nothing but it is a heuristic function. So it is a combination of UCS and best first search, which is used to solve the issue efficiently. Using the function h of n, which is a heuristic function, this search algorithm determines the shortest path using the search space. The search space is one of the parameters used to calculate the path. And A-star algorithm is similar to UCS, except that it uses G of n plus H of n instead of G of n. And this is the equation used to find the cost, where C of n is equals to C of n plus C of n comma 1. And H of n, M is the heuristic function, where and F of M compute the most reduced aggregate cost. And here are the time complexity and the space complexity for this search algorithm. Here are the few steps to calculate the path using the search algorithm. Initially, first we need to add the first node to the open list, which is the 1, and determine whether the open list is empty or not. If the list is empty, then it return to failure and quit. Uh, Choose the node from the open list with the shortest value of the evaluation function, which is a g plus h. If the node n is the target node, return success and stop. Otherwise, return failure and stop. Uh, and then extend node n and produce all its descendants, then add n to the closed list. First, we need to check whether each successor is already in the open and closed list or not. If not, compute an evaluation function for n and insert in it into the open list. If the node n is already in open and closed list, uh, it should be attached to the back pointer containing the lowest g of n value. And and later, like if node, yes, and again we need to repeat the step, and like we need to go back to the step 2 and repeat the same steps till step 6. So this is all about the A star search algorithm, which is a informed search algorithm. And the second one in informed search algorithms is a best first search, which is also called as a greedy search. And it is a combination of breadth first search and the depth first search algorithms. Here we use the priority queue to implement this algorithm. And here are the time complexity and the space complexity, where B is represented as branching factor and D is the solution depth. Here are the few steps used to calculate this search. First, we need to add the first node in the open list. And if the open list is empty, then we need to stop and return failure. Then move, if it is not empty, then we need to move the node n with the lowest h of n value from the open list to the closed list. Then we need to extend node n and construct node n's descendants. And later we need to examine each of node n descendants to see if any of them is a goal node. If any of the successor nodes is a goal node, return success and end the search. Otherwise, we need to go back to the, otherwise we need to move to the another step. Like for each successor node, the algorithm searches for evaluation function, which is a f of n, and determines whether the node was in the open or closed list. Then we need to again go back to the step 2 and start the process again. So this is all about the best first search, which is also called as a greedy search. While coming to the comparison of all these algorithms, so there are few parameters used to compare these: time complexity, space complexity, optimality, and completeness. So here we can observe in the diagram for each algorithm, here are the space complexity, time complexity, and also the optimality and completeness. What exactly the time complexity is? It is time taken by the algorithm to find the solution, and the space complexity is a memory required by the algorithm to perform the search process. And the optimality is defined to check the algorithm solution will be always be optimum or not. Well, coming to the last parameter, which is a completeness, it is a computation guarantee to find an answer when one would say it is. So this is the comparison, how we compare all these algorithms. So yeah, the next part will be continued by my teammate. Thank you.
Thank you. Now I am going to discuss on the paper related to severe weather avoidance using informed heuristic search. Next slide. What is informed heuristic search? Informed search algorithms are aware of the goal state, allowing for more efficient searching. In these algorithms, it is mainly based on heuristics, and it is also called as heuristic search. An estimate of the distance between cell and the target is called heuristic. The heuristic function calculates how near a state is to reaching the object, and it computes the cost of an optimum path between two states. It is also denoted by h of n. The heuristic value is always positive, and the best example for implementing heuristic function is A-star algorithm. And in this A-star search, it is also an informal technique which makes use of the evaluation function to determine the best path between the two nodes. Come to next slide. Free flight, it is a new system of managing air traffic. Usually, weather avoidance algorithms need to analyze the safety of the airplane in a free flighting in case of any severe weather conditions happen. Due to this, most of the researchers focused on improving its performance. So after the first departure limitation, free flight rules will start. It will stop with the start of the arrival sequence to the destination airport terminal space. There are different algorithms used for maintaining these free flight scenarios. They are Dijkstra and Bellman-Ford algorithm. These two algorithms are single source shortest path algorithms. These are optimized algorithms to solve this issue. We have A-star algorithm, which is used to determine the best path from one point to another point. Then coming to next slide. In this slide, we can see weather intensity ranges and different color codings for each range, etc. A destructive weather scenario refers to severe weather. This can be also called as localized storms. These localized storms are of strong wind shear, violent updrafts and downdrafts are dangerous and cause damage to aircraft. Above table shows different frequency ranges for each color. The usual rule of safe airplane navigation is to avoid places where intensity is greater than 30 decibels or equal to 30 decibels. As a result, the yellow and range areas are need to be avoided. It should be noted that there may be some ambiguity in the measurement of these range values because it's in an open environment. Coming to next slide. So, A-star algorithm. It is one of the best and popular technique used for pathfinding and graph traversing methods. So, it tracks all the paths that begin at the root node, and it enlarges such routes by extending one edge at a time. It runs till its termination requirement is met, that is the end node. So a lot of games and web-based maps use this algorithm for finding the shortest path efficiently. So it is also referred as a best first search algorithm. The function used to solve this algorithm is f of n is equal to g of n plus h of n, whereas g of n is the distance traveled from start to the cell, and h of n is the estimated distance from the cell to the target value. So a sufficient condition for obtaining the best solution is that estimated for the cost is smaller than the best possible value. So coming to next slide. Here we can see different stages involved in A-star search algorithm. As my teammate mentioned, there are different scenarios. We can go from start node to the end node. If there are multiple solutions available for one problem, the A-star search algorithm will efficiently provide the best solution among those solutions. So it can also offer so many different solutions as a result. So the best application, the best scenarios where A-star algorithm is implemented in AI pathfinding, image processing, network routing, and also in games environment. Coming to next slide. There are some constraints in developing these weather avoidance algorithm. Besides being shortest path that avoids severe weather, it need to be lie within some constraints imposed by threshold comfort level, pilot workload, and aircraft's physical limitations. There are minimum segment length, maximum turning angle, and minimum number of turns. The minimum segment length refers to the distance between any two vertices on the flight route must be higher than or equal to the present minimum distance. So this is essential to lower the pilot effort, and the aircraft should be allowed to complete one turn before beginning another. This is addressed in our paper by limiting the distance between two nodes. So coming to maximum turning angle, typical turns in the flight route have heading changes of less than 600, and it must not exceed 900 because it is the limit for that one. So that this limitation in our paper is restricted by number of nodes that may be formed from the particular node. So next one is minimum number of turns. The produced flight route should be symmetric continuous with as few turns as necessary. This is required in order to lessen the pilot's burden. So coming to next slide. So thunderstorm avoidance algorithm. In this algorithm, we have two nodes, one is starting node and ending node. The black region is where the thunderstorm present and it cannot accessible. A historic function is developed to determine the distance between node and its parent node. If there is a thunderstorm between a node and its parent node, the cost of the path is set to extremely high value. So the historic function comes in the picture here. It is the straight line distance from the starting location to the ending location. If a thunderstorm occurs along this path, a little deviation is applied to the straight line distance. And for handling all these memory locations, we are using a algorithm called simple memory based A star algorithm, that is SMA star. In SMA star, a specific amount of space is allocated to the storage of nodes. Once a node has been reached in the search tree, the best path from this node to the terminal node is independent of the path followed in reaching this node. So A star searches are conducted separately for path to the left of the thunderstorm and on the path to the right of the thunderstorm, and it will give you the output the best path. So the memory of the best forgotten path is also kept in SMA star such to avoid a regeneration of the same node. The downside of the SMA star search is that if the allocated memory is less than the memory necessary for the best path of the destination node, the results produced by these are suboptimal, or in worst scenario, there might be no solution from this scenario. So now my teammate will continue with the results of these algorithms.
So, hello all, my name is Murali Krishna Bomsetti. So, I'll be continuing the remaining part of this paper. So, the algorithm developed above is applied to some of the sample cases. In this case, the grid size is 1 mile by 1 mile. In the first case, the radar image of a stationary thunderstorm is shown in figure 4. So, you can see this is a figure 4, and the flight path can be seen. So, this is the flight path which we can see. Using the definitions above, the inaccessible region is determined and the shortest flight path between the point 1 and point 2 is obtained. Point 1 and point 2 is obtained. The shaded portion of the figure 5 shows the accessible portion corresponding to the radar image of figure 4. Figure 6 shows the flight path with respect to the inaccessible regions, and the figure 7 shows the flight path with the radar image. The minimum segment length in this case is 8 units, that is 8 miles on the radar image. The detour shown in figure is the flight path directed by the weather avoidance algorithm for case 1. The minimum segment length chosen for case 2 is 10 units. So here we have chosen 10 units, that is 10 miles on the radar image. For the second case in figure 8, the original flight path from point 1 to point 2 goes through the thunderstorm. The algorithm takes 11.11 seconds to compute the safest path when run on a Pentium second PC. In the case 3, a line of 3 stationary thunderstorms lies in the original flight path as seen in figure 9. So here you can see is in figure 9. Point 1 and point 2 shows the flight path directed by the thunderstorm avoidance algorithm in figure, and as can be seen, it avoids the regions of intense thunderstorm activity. The minimum segment length in this case is 8 units, that is 8 miles on the radar image, and it takes 15.25 seconds to compute the safest path. The thunderstorm avoidance algorithm computes a new heading for the airplane, depending upon the current radar image. The time interval between the two consecutive heading changes is the smaller of A, the time taken by the algorithm to compute the new heading, or B, 10 seconds. So it will be either A or B. For the interval between the two consecutive headings, the airplane maintains a constant velocity. In the remaining two cases, both the airplane and the thunderstorms are assumed to be moving at a constant speed. Figures 10 and 11 shows the results of simulation for cases 4 and 5 respectively. The dotted contours show the intensity of thunderstorms while the airplane is at starting point 1, and solid contours represent intensity after reaching the terminal point 2. You can see here like figure 10 and 11. In case 4, a 3-line thunderstorm is moving in the positive x direction at a speed of 40 miles per hour. The airplane is moving from point 1 to point 2 at a constant speed of 150 knots. Figure 10 shows the path followed by the airplane in this case. In case 5, a line of thunderstorms similar to a squall line is heading in the negative x direction of a speed of 50 miles per hour. In figure 11, 1 is the starting point and 2 is the ending point, and the actual path followed by the plane can also be seen here. In cases 1, 2, and 3, the algorithm computes the safest and shortest path between 2 points successfully, and the amount of time it takes is reasonable. Results in cases 4 and 5 demonstrate the effectiveness of the algorithm in the event of moving thunderstorms. In both cases, the airplane safely avoids the regions bounded by the red contours or the regions of intense weather activity. So it tries to avoid the area where it has a high red color because it has thunderstorm in it. So algorithm convergence and stability. The algorithm works well if given a small area on the map, but its functionally in a large sample area still needs to be established. Safer roads can be obtained by changing the limit to say 20 dBz, through which would mean larger deviations from the original flight path. Another way to avoid coming very close to yellow and red regions on the radar is to specify the minimum distance that should separate the inaccessible region and node closest to the boundary of the disrupted zone. Algorithm fails to compute safe detours if the starting point of the path lies inside the region of intense thunderstorm activity. The algorithm always tries to find the solution in the forwarded direction. So in the event of being flanked or by thunderstorms along all of the forwarding heading directions, the algorithm cannot retrace a path to get back away from the thunderstorm. If the algorithm regions within intensity greater than 25 dBz are set as inaccessible, safer routes can be obtained by changing the limits to say 20 dBz. Through that would mean larger deviations from original flight path. Another way to avoid coming very close to yellow and red regions on radar image is by specifying the minimum distance that should separate the inaccessible region and node closest to the boundary of the disrupted zone. The algorithm works well if a given small area on the map, but its functionality in larger sample areas still needs to be established. Given the minimum segment length and minimum number of turns, the algorithm succeeds in finding the solution. It should have the ability to change the minimum segment length depending upon the size of the thunderstorm. With this capability, it will provide a greater flexibility in choosing the turn points in the flight path. Finer grid sizes will give shorter routes, but it can make the algorithm computationally too expensive. So finally, coming to the summary, in this paper, a severe avoidance an algorithm has been developed for general aviation. The algorithm uses the principle of A-star search, which is an algorithm, and suitable modifications are made along the lines of SMA, one more algorithm search technique to reduce the time and space requirements. The modeling of the problem ensures that if the underlying assumptions are true, the algorithm will succeed in generating a safe flight path. The results show that the algorithm successfully computes the safest and shortest path in simple area on the map. The simulation results are encouraging as well, though better results can be ensured by further turning the algorithm. So that's it from our end. Thank you.
Thank you, everyone.